Okay, and we're back for the loadable registers question. So in this question, there is a big drawing on the top, which can be kind of confusing, and then there's all of these timing diagrams in the bottom. So let's pick through them, talk about what's important, and see if we can figure out how to do this one. So the question says, complete the circuit diagram below for a left shift, right shift register. So we see this, and it has input left and input right. Let me make my pen a little bit smaller. And we have 3 bits, Q2, Q1, and Q0. Okay, and then it looks like we have some different options. So we have 0, 0, 0, 1, 1, 0, and 1, 1, and we can see what those different things do. So basically, here we have our commands. So these are our commands. So I'll label that commands. And those commands are controlled by C1 and C2. And so the way you can imagine that is if you had 2 switches or 2 buttons, you could tell this system what to do by flipping those switches in a certain orientation. And so the different commands are clear, left shift, right shift, and hold. We'll talk about all of those in a minute. But all you need to know are, okay, these are the commands, and these are the times that we do the commands. Or when we get these inputs, these are the things that we need to do to the data. And so we can take this, the command section, and we can do the top, and then we can take the command section and do the bottom. And it's not super important to use this part up here to do the timing diagrams in the bottom. You could use it if you wanted to, but for this part, it's easier to do the top part by itself and then do the bottom part separately. So let's remove some of this, and let's look at what the commands are. So these different commands, so let's talk about 0, 0, clear. All that will do is it will change Q2, Q1, and Q0. It will set them to 0, 0, 0. That one's pretty simple. And hold is also simple. So 1, 1, hold. All that one does is it keeps everything the same. Q2, Q1, and Q0. But now we have to see, okay, what does left shift and right shift do? So let's do left shift, 0, 1. I'll abbreviate that LS for left shift. So when we move things to the left, we're going to get Q0 and Q1, and then we can read over here that serial in right goes into Q0, so I'll abbreviate that as SR. Oh, I guess let's do SIR, serial in right. And what you'll notice is, I'll mark this in yellow, that these 2 bits, Q1 and Q0, slid to the left and filled in the spots where Q2 and Q1 were, and I'm just now noticing that I did label those in the wrong order. That should be Q1 and Q0. Sorry if I confused any of you on that. So similarly on right shift, so this is 1, 0. I'll do RS for right shift. The Q2 and Q1 are going to slide to the right, and serial in left will slide in to Q2. And then I know over here it does say Q3 right here. That is a typo. It should say Q2. But for this, what you'll notice is that Q1 and Q2 slide to the right and fill in the spots of Q1 and Q0. And so there are different types of left shift. There's sometimes where it will do circular shifting, which you guys will do, I think, coming up on a quiz. And so circular shifting, instead of eliminating one of the bits and replacing it with something like here we can see that we slid to the left, and when we went to the left, we lost Q2, and then one of those bits was replaced by a new input. In circular shifting, the bits will wrap around, so then Q2 would then fill in the spot of Q0, and that'll come up on the next assignment. But for now, all we have to do is figure out what to do with this drawing on the top. So for this, all we're going to do is connect lines, or draw a bunch of lines on this, connecting these outputs to these inputs, in the correct order. So what I'm going to do is I'm going to solve or draw all the lines for this one, and then from there I'll leave you to do the rest of them. So let's do this, and we'll do them all in different colors. We'll do blue. So for 0, 0, we're going to clear. And so what we'll notice is, here, let me remove some of these circles. So we have Q2, oops, still on eraser. Q2 becomes a 0. So all we have to do is put a 0 in. So we put a 0 in to the 0, 0 spot. And so for anyone that's figuring it out already, this one will also be a 0, and this one will also be a 0. And so the way that it works is when 0, 0 is put in, meaning these 2 bits are there, that means our commands are 0, 0 on all of these. And that means you can imagine it as like there's a wire connecting it to 0, 0, which means D is connected to 0, so D is a 0. And then when the clock goes high, the 0 becomes, or goes into the spot of Q2. And it'll clear out the data. So let's remove some of that extra stuff. Okay, so now let's do hold first, because hold's a little bit easier. What we'll notice here is that for Q2, the input is Q2. So in order to do that, all we have to do is connect the output of Q2 to the input. And so because we're on command 1, we will draw a line that loops back around and feeds itself in to 1, 1. So that means when the clock goes high, Q2 will go back into Q2, and therefore I won't change anything, and that's exactly what hold is supposed to do. It just doesn't change anything. Okay, moving on. Let's do left shift. So for left shift, we'll do this in yellow. What we'll notice is that Q2 becomes Q1. So all we have to do is take the output of Q1 and draw a line that connects it back into 0, 1, because we're on command 0, 1, and Q2 becomes Q1. And for right shift, the last one, what we'll notice is that Q2 is connected to serial in left. So all we have to do is draw a line from serial in left into 0, 1, and we are done with about a third of that top section. So I'll leave it up to you to do the rest of them. It's not super tricky once you figure out how to do it. The harder ones are left shift and right shift, but I'm sure you can figure it out. Okay, so moving on to the lower portion of this, we see here that we have a timing diagram. And if you watched the first video, you remember that I drew a bunch of vertical lines going down like this. And so what you'll notice here is that all of these vertical lines line up with these X's on the bottom. And the reason that this is set up like this is because these are the times that output Q can change. When the clock changes, Q can change. If the clock if we're in between clock cycles, the output can't change because the flip-flops will not change. So the way this is set up for you is they have already marked the times where output Q can change, and so these vertical lines are not as useful, but you still can, if you want to, draw them down like this, just to give you a frame of reference of where they are hitting in terms of serial in left and serial in right. So what I'm going to do is just go through, oh, those are backwards, and label all of these 0, 1, 0, 1, 0. So that will just help us remember what those values represent at certain times. And if you want, you can go through and you can label these commands, because these are your commands. So these are your inputs and these are your outputs. And so what we have here are 2 bits, which represent C1 and C2, and then 3 bits, which are Q2, Q1, and Q0, respectively. And so what we're going to do is we're going to write things in each of these boxes for what those, or sorry, we're going to fill in those boxes with the values of Q1, Q2, and Q0 at certain times along this timing diagram. So let me go ahead. Let's erase some of this stuff. And let's work on the first one. So 0, 0 is our first command, and that is clear. So we'll write that in. You don't have to write it in, but I'm going to do it just to keep track of what's going on. And so that means that this is our command, and at that time, we're going to clear the data. So the data started with 1, 0, 1, and we're going to clear it. So because we're clearing it, we know that everything gets set to 0. And so at this time, you could go back and reference the circuit diagram at the beginning, but if you already understand what the commands are doing, then it's not as important to reference the circuit diagram if you can just see the commands and know what they do. So the next command is 0, 1, which is a left shift. So we'll put ls right there. And so on a left shift, we know that things are going to slide to the left. So these two zeros will move into here as the first two zeros, and then a new bit will come in, and that new bit will be serial in right. And so in this case, serial in right is a 1, because at this time, serial in right is a 1, and so we are going to get a 1 as our newest bit. So now we look again, and our next command is left shift, and so we are going to move our 2 bits to the left. So this 0 and that 1 will move into here. Oh, let's do this in black. 0, 1 represent those 2 bits, and the newest bit that will fall into the missing space will again be serial in left, but this time serial in left is a 0. And so because it's a 0, we fill it in, and we get 0, 1, 0. So I'll leave it up to you to fill in these last 3 spaces, and then after that, you're done with this part of the assignment. And then as a final note, let's move down to, see if I can get to the next page. The rest of this assignment is about Arduinos. And so for this, you just have to go to this, this PDF and read through it. It tells you what pages the answers are on. And most of them are in there. But for right now, I just wanted to talk about question number 4. So question number 4 is the only one in here where you have to do any actual computing, and it says that in the question. It says using the answer above. So we're going to look at question 3, and your brain, you have to figure out a certain amount of, so the question is, it says how many address bits are required to address a byte in each type of memory. So what will happen is in question 3, you'll go in and you'll read this table and you'll fill in this data. And so let's say you get something like, 12,000 bytes. So this says how many bytes of each memory. So in this certain Arduino, it has different types of memory, and so let's say that you have 12,000 bytes of flash memory. So this next question is asking how many address bits are required to address a byte in each type of memory. So if we're talking about flash memory, we know that there would be, for my example, 12,000 bytes. And so if we're going to address 12,000 bytes, 1 byte at a time, that means we need 12,000 addresses. So a way you can imagine that is an address is like a little container. And so we would have address 1, 2, 3. Sorry, that was a horrible 3. Let's make that better. And then it would continue on and on and on until we got to address 12,000. And so the question is, okay, so in each of these, each of them contains a byte, and I'll label that as capital B. But each of them also has an address, meaning each of them has its own specific number. And so the question boils down to how many bits do I need to represent the biggest number in this address block. And so in this case, we would have to represent numbers as small as 1 and represent numbers as big as 12,000. And so in order to do that, we would say, okay, 2 to the n is equal to 12,000. And then you'd solve that equation, and it would be like 10 or maybe 11 bits, something like that. And that would be your answer. You'd say, oh, it takes 11 bits. And so that means that 11 bits can be used to address 12,000 kilobytes as long as they're divided up into chunks of 1 byte at a time. So hopefully that will help you get through this one. The rest of these you should be able to pull out of the PDF. If you have any questions, you can always let the TAs know.